This is section 7.1, day 2, and we're talking about different applications of net change or rates of changes. And we are going to be given some application problems where you're given the rate of change, and that is like the derivative function. And that's really what you have to discern in a lot of these problems is what function are they giving us. So in this problem I highlighted, this is by the way the famous potato eating problem, the rate of potato consumption, which is eating, was given by this function, so that's a rate. And you want to know how many bushels of something or what the quantity of the item is, you're going to have to take the antiderivative. Okay, so we have a model for rate of consumption, and then they want us to figure out how much it was from January 72 to December of 73. Okay, so this is year t equals 2, and this takes us to the end of year t equals 3. So we're going to take the consumption of 4 from 2 to 4 years because it says 1970 to 80. So our potatoes equal the antiderivative, the area under the curve of the rate. And you're going to take CT dt. And this is a good way to write this when you're doing an AP test too. You don't have to copy the entire function. Go ahead and just write whatever name they've given the function. In this case, it's consumption. This time, we're just going to use the, because we don't really know how to take the well, yes, I guess we do. But anyway, well, maybe we don't, I don't know. We're going to just put this in our calculator. So, and that's fair to do if you're on a calculator part of the AP test. All right, so put this in your calculator and you should get 7.066. And this is in bushels, millions of bushels. Okay, so this is millions of bushels. That's how many potatoes were consumed. All right, famous problem. The next famous problem is number 6 on page 384, and this is using a table. So this table's in your book. A pump is connected to a generator that they pump the rate in gallons per minute. So you have this column is time, this column is your rate, gallons per minute. What we're going to have to use on this is the trapezoid rule. So don't forget that trapezoid rule because that gives you area under the curve. And that will give you, if this is the rate, which it is, it will give you the gallons because this shows us gallons per minute in our table. If we take the antiderivative of that function, which is the area under the curve, we will be able to find the number of gallons. So let's do that taking the trapezoid rule. T equals, okay, so it says that our interval is 5, therefore H is 5. So don't forget, like you did back on the test on trapezoid rule, that it's the interval divided by 2. Okay, now trapezoid rule says you take the first number in the rate, which is 58, and you add that to 2 times the second number, 2 times the third, 2 times the fourth. So multiply 2 times all those middle numbers, 60 plus 65 plus 64, and all the way down here until you get to the last one. What is the last one? 63. And then you just add 163. So you multiply 2 times all the middle numbers, put the 2 ends out there. All right, now if you calculate all this, actually, for some reason on my paper I've used gallons, GT, as a little function here. The number of gallons are 3582 and a half. I hope I didn't round that to a half. And this is gallons. And that's how many were pumped in that hour, during that hour. Okay? Last but not least, we're going to do a little problem on Hooke's Law. If you guys have had some physics, you might have seen this. I am by no means an expert on Hooke's Law, but this is Hooke's Law. The spring goes up and down, and K is a constant. That's always good to know. K is a constant. If you have the f of x, which is the force of the spring, you can find the work done by taking the antiderivative of the force. So work equals, why am I rewriting that? I've already got it up here. Work equals the antiderivative of the force. So we need to figure out the function first of all. And they tell us that a force of 10 newtons, so we have F equals K times X. Let me do this over here and move it. F equals K times X. The force is 10. We really need to find out what K is. X is the distance the spring moved. So we have force equals the constant times the distance the spring moved. I'm using this and this. So therefore K is going to equal 10 over 2, or 5. And I believe they measure this in what are called, newtons per meter, I guess. I used to know physics, but no more. So our function, f of x, why do I keep doing this? Our function is going to be equal to k, which is 5, times x. That's our general function for this spring, based on that one little pull down that we had. So let's figure out what the work is then. The work when you're stretching 4 meters from its natural length. So we're going to put that f of x function in here, the force function, which is 5x. And we're actually going to evaluate that from 0 to 4, because the spring is going to go from 0 to 4 meters. All right, the work is equal to, how nice that we know how to take this antiderivative, 5x squared over 2, evaluate it from 0 to 4, and you should get 40 Newton meters. I think that's the unit. All right, so that is Hooke's Law, little ditty on Hooke's Law, and that's all we have for today. So, happy problems.